So here we are in our last video for chapter 26 with the chi-square tests, and this time it's going to be a subtle change from the chi-square two-way test, and now we're going to, instead of looking at homogeneity, we're going to be looking at independence. And if this brings back flashbacks to probability, this is a different way that we can test for independence between variables. So earlier in this year, we discussed the idea of independent variables and the contingency tables used to show the various conditions of the variable. Earlier, I mentioned that in a chi-squared test for homogeneity, we used a contingency table. We've seen those before. As a refresher, contingency tables categorize counts on two or more variables so that we can see whether the distribution of counts on one variable is contingent on the other. Think probability of A given B. A test of whether the two categorical variables are independent examines the distribution of counts for one group of individuals, so one sample, classified according to both variables in the contingency table. A chi-square test of independence uses the exact same calculation as a test of homogeneity. The only difference is how you consider the data. So let's get a little more specific. In the test of independence, subjects are collected at random from a population, and two categorical variables are observed for each observation. In the test of homogeneity, the data are collected by randomly sampling from each subgroup separately. The null hypothesis is that each subgroup shares the same distribution of another categorical variable. So those are the distinctions. Now, as always, we look at our assumptions and conditions. We still need the counts and enough data so that the expected values are at least 5 in each cell. If we're interested in the independence of variables, we usually want to generalize from the data to some population, which does mean that we need to check for randomization. So in that case, we'll need to check the data that they are a representative random sample from the population and that the total counts are less than 10%. Remember, when you have to check these, it's because you're looking to generalize. Each cell of a contingency table contributes a term to the chi-squared sum, as we've seen. And then, as always, it's informative to examine the standardized residuals, as we did for the chi-squared test for homogeneity. So some words of caution before we move on to our last example problem. As you've now seen with a couple examples that we've done, chi-square tests are relatively simple to do and easy to understand. So the tests are common and the tests for independence are probably the most common tests that we do. Remember that a small p-value is not proof of causation, and that's the danger that a lot of people get into. Chi-square tests make no claim to causation. They only measure different or not so different. Since the chi-square test for independence treats the two variables symmetrically, we cannot differentiate the direction of any possible causation, even if it existed. So be careful not to speculate on reasons for the lack of independence. Confounding variables cannot be accounted for in the chi-square test, things that we can't separate out. Two categorical variables can fail the test of independence in many ways. Examining the standardized residuals can suggest possible underlying patterns, and that's why it's important that we look at those standardized values. Other words of caution. Do not be trapped into assuming numbers in the table are counts. Chi-squared tests require counts, not proportions, not percentages, not measures, just counts. Just because you have numbers in a two-way table does not make them appropriate for a chi-square test. Also, beware of large samples. You might be saying, what? Similar to two-way tests with very large power, when you have very large samples, a chi-square test will nearly always reject the null. So we have to be aware of large samples. Avoid using the word depends when referring to variable conditions. Dependence infers causality. Better to use the word contingent or contingent upon. Variables that are not independent are not necessarily dependent. They are simply correlated. Remember, association is not causation. So let's look at our last example for this unit. Let us look at handedness and eye color. So do you think these variables are independent? Do you think people's eye color is independent of people being left-handed or right-handed? As always, with a test, we have to make a hypothesis. So our null hypothesis in this situation. Handedness and eye color are independent. That's our null. Our alternate hypothesis says there is an association between handedness and eye color. Just like before we go to the test, we need to check our assumptions and conditions. So the counted data expectation. We look at our chart and all of these values are counts. So we're good. Next, we look at the independence assumption. The counts in the cells are certainly independent of each other. Next, the randomization condition. The individuals counted and available for testing must be a random sample from some population. And then next, we have to look at the expected cell frequency condition. And we must expect to see at least 5 individuals in each cell. Now, if we look at just the observed data, we get 2 problems. Green and other are lower than 5. So we immediately have a problem. And we need to check our expected values. Now you see this in our table, but just as a refresher, how do you calculate those expected values? So first we need to take our table, and we have eye color and left or right-handed. So if we summed up each one of the rows, 6 plus 36 is 42, 7 and 26 is 33, 23 for green, and 16 for other. And likewise, if we calculated the column, we would get 19 left-handed and 95 right-handed. To calculate the expected value, if you forgot, we take the column total times the row total and divide that by 114, which is the grand total. Likewise, for right brown eyes, we would have 95 times 42 all over 114. And if you did that work for each one of these cells, we would get 7, 35, 5.5, 3.83, 19.17, and 2.67, and 13.33. So what I'm going to do is write this in our two-way table that has both our observed value and our expected value. So you might see this, and this is kind of the appropriate way. So our observed value is 6, our expected value is 7. 36, 35, speed this up. And here's our issue again. So if we're looking for our expected counts, we see that green and other are both underneath what we want them to be. And so what we're going to end up doing by getting around that is just combining green and other together. And if you go 3 plus 2, that's going to be 5. So our other category is just going to throw green in all together. And now we see that we have brown eyes, blue eyes, and other. Each of those counts are above 5 for both the observed and the expected. And now we are good to go. So lastly, if we want, we have 3 rows and 2 columns. So that gives us our degrees of freedom. 3 minus 1 times 2 minus 1 is 2. And now we're going to jump over to our calculator and we're going to type in our matrix. So I want this one right here. This allows me to type in what we want. We said we have 3 rows and we have 2 columns. We are going to type in our observed data. So we have 6, 36, 7, 26, 6, 33. And again, we have to store this as a matrix so we can call it later. So there's my matrix. And now I'm going to do my chi-squared two-way test. So I hit menu. 6 for statistics, 7 for tests, and this one is 8 for a two-way test. All I need to do is tell it what matrix we're going to. And there we get our chi-squared statistic of 0.708, and we get our p-value of 0.701 with a degrees of freedom of 2. Lastly, what we want to look at is if we go vars for variables and our stat expected matrix, and then we're going to store that as B. There's all of my expected values that we calculated. And then also, what I want to look at is the component matrix. So I'm going to hit vars stat comp matrix. And again, we're going to store that in C. So these give me the components for each one of the values contributing to our chi-squared statistic. If we look at the calculation of the chi-squared statistic, we take the observed value minus the expected value squared all over the expected value. And summing all of those up gives me my chi-squared statistic. And lastly, we're left with making an analysis. So our p-value here is 0.7017. And that is definitely greater than a standard significant level of 0.05, which means we fail to reject the null hypothesis. And leaves us with our conclusion. There is not sufficient evidence to conclude there is an association between eye color and handedness in high school students. So I hope these videos were helpful. Make sure you work on the homework, the quiz, and the free response question. And there will be office hours in case you need any help. Good luck.